All right. Thank you everyone for coming. This is the IIF Distinguished Lecture Series. This is the first one offered by Professor Rob Hyndman. My name is Tao Hong. I'm a professor from University of North Carolina, Charlotte. I'm on the board of IIF. This is one of our recent initiatives. I'll have the honor to introduce Professor Rob Hyndman. Rob Hyndman is a professor of statistics in the Department of Econometrics and Business Statistics at Monash University. He's an elected fellow of both Australian Academy of Science and the Academy of Social Sciences. He's the author of over 200 research papers and 5 books in statistical science. He's also an IIF fellow. He was a former editor-in-chief of International Journal of Forecastings. He has many achievements in forecasting and broader areas. So in the next few lectures, he will be sharing with us hierarchical forecasting. All right, thank you, Rob. So please go ahead.
Thank you, Tao, and it's an honor to be able to be the first of the first lecture in this series of the IIF. So let me start by sharing my screen. Okay, so yeah, for the next 4 lectures, we're going to talk about forecast reconciliation. If you want the slides, the URL's down here at the bottom of the screen. Just go to robjhyndman.com/FR2023, standing for Forecast Reconciliation 2023. So as I said, there's going to be 4 lectures. So today we're going to talk about the concepts of hierarchical time series and forecast reconciliation, and then we'll look at some perspectives later in the week from different ways people have thought about the subject. And then next week we'll do probabilistic forecast reconciliation and then temporal and cross-temporal. I'll put the dates in there. It depends on which part of the world you're in to what the date is. So it's the 7th here in Australia, but it's the 6th in Europe and North America. So let's talk about hierarchical time series data. So I'm going to start with some examples. So I first started thinking about this problem nearly 20 years ago. And the context in which I was thinking about it was classification of occupations, where different occupations are divided into groups and then into smaller groups and then smaller groups again and so on. And for example, I'm a statistician, and in the statistical profession, we are inside the group of professionals, and then within that, business, human resource and marketing professionals, and then information and organizational professionals, actuaries, mathematicians and statisticians, and then statistician. So you can see there's this hierarchy of organizations. And if you're going to do forecasting of different organizational groups, you want the forecasts for actuaries, mathematicians and statisticians to be the sum of the forecasts of the people that are within the various subgroups there, and so on. Then I came across it again a couple of years later when I was doing some work for a pharmaceutical company, and they were interested in forecasting different types of drugs. And drugs around the world are classified using the ATC drug classification. And so they're divided into groups, and then each of those are divided into smaller classes, and then they're divided again, and so on. And so if you're doing drug forecasting, you need to make sure your forecasts for the lower levels add up to the forecasts for the upper levels. And then a bit later on, I was working with a spectacle manufacturer, and they were looking at sales of spectacles, and they had they classified their different spectacles by brand, by gender, by price range, by materials, and then by stores. And stores were within countries. And so you have a lot of different disaggregation factors that they wanted to deal with, but they wanted the forecast to add up so that the forecasts for all the different brands added up to the total forecast, or the forecast for different countries added up to the total forecast, and so on. And when you disaggregate enough, you end up with a lot of series, and those series tend to be quite noisy and they're difficult to forecast. So the problem comes up a lot in a lot of different contexts. And as I said, I started thinking about this 20 years ago. And at that stage, there were very limited tools available to be able to handle this problem. So what I want to do today is just to introduce the problem and the tools that were available at the time, and then the first steps that have been made in the literature over the last maybe 10 to 15 years to try to solve it. And then my next example, which is one that will come up quite a lot, is to do with forecasting Australian tourism. And so here you want to forecast national tourist numbers, and then you want to forecast them by state, and then by zone or region, and so on. Then you want those forecasts to add up. So we have data on this from a widespread survey, and through that survey, the government estimates how many tourists there are in the different regions, zones, and states, and also why they're there. Are they traveling for different purposes? So just to show you what this example looks like, and to give you a bit of a intuition about why it becomes more difficult to forecast as you get more disaggregated, here is the total domestic travel in Australia, monthly data over a few years, and you can see it's quite a strong seasonal pattern, an unusual seasonal pattern with some big spikes and troughs, but those happen every single year, which means that if you build a seasonal model, you can forecast this reasonably well. And there's some trends, but if you were trying to forecast the next year of this data set, it wouldn't be too difficult to find a model that fitted the local trend, picked up some seasonality, and then produced some forecasts. If we disaggregate by state, we see a couple of things. One, they get a little more noisy. And secondly, the states don't all behave in the same way. So if you look down at the bottom two series down here, the bottom one is Western Australia, the huge state on the west side of Australia. And you can see that it's the trough here is happening in summer, and then the peak is happening in winter. Whereas the pink one, which is Tasmania, the most southerly state in Australia, that's reversed. The peak's happening in summer and the trough's happening in winter. That's because of the, Tasmania's being in the south of the country is a cold place, and so you generally want to go there in summer. So you get this out of phase thing happening. So if you just forecasted the most aggregated level and disaggregated those forecasts, you're not going to get good forecasts because of the not taking into account the phase shifts that are happening. If we disaggregate down a little further, it gets even noisier. And then all the way down to region level, you see that data is very, very noisy, which makes it hard to build any kind of statistical model that's going to be good here. And generally, we see that happening with all of these types of examples. The more you disaggregate, the noisier it gets. But if you aggregate too far, then you sometimes lose some of the important signal information. So we can think of this in a graph structure, where a hierarchical time series is a collection of time series, and they are linked in this structure where the total here has to add up to its components, and each of those components has to be the sum of the components below, and so on. So examples where it's strictly hierarchical in this manner would be tourism split by state and then by region, or if you're a retail outlet, sales split by product groups and subgroups right down to the smallest units, which are normally stock keeping units or SKUs. They don't have to be strictly hierarchical though. A grouped time series can be a collection of time series that are grouped in some non-hierarchical ways. And some of the examples that we started with are like this. So if you split tourism by state and by purpose of travel, then they are not naturally nested within each other. You can split tourism by state and then by purpose of travel, or you can split tourism by purpose of travel and then by state. So you could write this as two distinct hierarchies. The same happens if you've got retail sales that are split by products and subgroups, and also by countries and regions. The regions are nested within countries and the subgroups are nested within groups, but the two are not nested within each other. They're sort of separate factors. So we call that a grouped time series rather than a hierarchical time series, although sometimes we use the term hierarchical time series to cover all of these types of examples. doesn't really matter because all of them can be written using the same mathematical notation. So this is the notation you'll see quite a lot. The y bold is a vector of all of the series that you're interested in. The aggregates and the disaggregates all together in the same long vector of series. And the B, the red B here, is the most disaggregated series. So in this tiny little example I've got over on the right-hand side, not a practical example because normally you would have many more series than this, but a good one to start with because it helps us think through the notation. We've got 3 bottom level series at the most disaggregated level. The sum of those gives us the total. So there's 4 series in total, and they are given by this 4 vector here, where you've got the total at the top and then the 3 disaggregated series at the bottom. And we can write that using this notation, this S matrix multiplied by the bottom level series. And the S matrix just shows how you combine the bottom level series to give the series that form the whole vector. So the top of it that has a row of 1s like this, because we are just adding up all of the series here. And then the next row just says grab the series A, and the next one grab the series B, and then the next one grab the series C. And that will give us all 4 series in the Y vector. So remember the notation, the bold Y is all of the data, the bold B is just the most disaggregated series, and the S matrix is a summing matrix because it shows how you sum the bottom level to get the entire series. Let's just demonstrate that this notation actually works for the examples that we've looked at so far. So here we have a bigger example where we've now got 9 of the disaggregated series and 2 aggregated levels in the hierarchy. And we can write that in the same fashion. We can put all 13 series together into the Y vector. And then the S matrix is this big collection of 1s and 0s, which allows us to add up the bottom level series to get the top level. So you can see that the first row here, it's just all 1s again because you want to add everything up. The second row is the first 3 are 1s and then the rest are 0s because we're just adding up the first 3 rows of the B vector and so on. And if I had a situation where I had 2 grouping factors which were not nested in any way, so I'm interested in row sums and column sums, then I can still represent it using the same notation, where all of them added together gives me the total. A and B added to these 2 added together in this manner gives me A. These 2 added together, these ones here, gives me the B. And if I want to sum in the other direction, I want to sum AX and BX, then I just have to grab that one and that one, which you do by putting a 1 there and a 1 there. So as long as you can write down how to sum up the things in the bottom level, you can write it down in this notation, Y equals S times B. So the idea of hierarchical forecasting is you want the forecasts at all the levels of aggregation to be summed up in a consistent way. So if you model and forecast all of the series separately, they will not generally add up. There's some special cases where they will, but in general, you'll fit models to each of the individual series at the disaggregated level and at the middle levels and at the bottom level. And then, but those will not be consistent with each other. We call that coherent. They'll be not coherent with each other. So we need to impose constraints on the forecast to ensure that they are coherent. And we want to do that in a computationally efficient manner because we do have often thousands or millions of series to deal with. Okay, so that's the general context of the problem and the notation that we can use to describe the data, the individual observations at each time t. Now let's step back a little bit and think about the history of this problem. and what people did up until 15 to 20 years ago. So this is what it looked like 20 years ago. We had, and I'm just using the tourism data here as an example. You had the top level series, you had the bottom level series, and sometimes you had series in the middle. And there were basically two main approaches. There was the bottom-up approach, which said, let's just forecast the most disaggregated series and then add up those forecasts to get forecasts for the other series. The top-down approach was the opposite. It said, let's just forecast the most aggregated series and then proportionally disaggregate those forecasts to get forecasts for the lower level series. And then the most sophisticated approach was to pick some middle level and forecast at that level and then do a disaggregation for the levels below and an aggregation for the levels above. And that was called middle out. And when I was doing consulting in the 1990s and the early 2000s, usually the question people were asking was, what level should I be forecasting at? What's the right level to pick for this middle out process? And I kept coming across this and thinking there's got to be a better way to think about this problem. Let me just talk a little bit about those two major approaches. Top-down forecasting generally worked pretty well for the higher levels of the aggregation. Like if I was forecasting tourism numbers, it would give me a good forecast for national tourism, but it would give me pretty bad forecasts for the ones below. It was simple because I just had to build one model. And if I had low count data, then it tended to work okay, again, for the higher levels mostly. But you lost a lot of information, especially when you had things like the different states have different seasonal patterns. You sort of lose that information. And the distribution of the forecast to lower levels it's not always straightforward, and it only really worked if it was strictly hierarchical. If you have different grouping factors, then you can't really do this properly. Plus, of course, there was no way of getting prediction intervals. On the other hand, bottom-up forecasting didn't lose any information because you were using all of the data at the most disaggregated level. So it captured the dynamics of the individual series quite well. But you had a lot of series then to forecast. And those series are noisy. Like they often just have zeros and ones and twos in them if you disaggregate enough. And so it's really hard to build a good model there. And again, there was no prediction intervals. So let's try and write down the problem using a little bit of notation. I'm going to put a hat on it to mean a forecast, a point forecast. We'll deal with probabilistic forecasts next week. So I put a hat on it to mean a point forecast. The subscript t plus h gives me the time ahead that I'm trying to forecast to. And the notation bar t like that tells me what I'm conditioning on. So I'm going to say I know data up until time t, and I'm trying to forecast 8 steps ahead. So that's my vector of forecasts, and I'll put them in the same order of y, and they're not going to add up generally. I'm going to fit different models to different series, and they won't add up. Then any coherent set of forecasts must be of this form. Y, I'm going to call this y tilde, that has to be equal to S times some matrix G times those original y hat forecasts. And the top down and the bottom up approaches and the middle out approaches can all be written like this, where we just have to choose the G appropriately. So G is, what's happening with G is it's grabbing whichever bits of the y hat we want to use, whether it's the top bits or the bottom bits. And then S is adding them up. So let's see some examples and you'll see why this notation works. If I'm doing bottom-up forecasting, then I want to grab the most bottom level series. So the G is simply 0 with an identity. So it just says grab the bottom part of the y hat matrix and then add them up. And that will give me the forecasts that are consistent or coherent but it's only using the bottom level series. On the other hand, if I did top-down forecasting, I would just want to grab the top series and proportionally disaggregate them. So I can make this G matrix look like this, where P is the vector of proportions that I grab from my top series and disaggregate down. So P1, for example, is the proportion of the aggregate that I want to give to the first disaggregated series. P2 is the proportion of the top series that I want to give to the second one, and so on. And then I get that will give me the proportions for each of the bottom level series, and I add them up again to get all of the other series. And as long as those P's sum to 1, that's going to work. That's going to give me a top-down approach to forecasting. So both of them can be written in the same notation. Y tilde is equal to S times G times Y hat. Now, I'm happy to take questions as we go. And I see that Sukanta Basu has raised his hand. So I wonder if we can... Okay, you should be able to unmute yourself.
Yeah, so I was, can you hear me?
Yes, fine.
Yeah, so my question is, like, when you are doing the middle out, will there be the similar way you can write down the, like what you are doing in the case of the summation of the probabilities equals to 1? What will be the equivalent in the case of the midway, the option?
Yeah, no, good question. And yes, you can do it in the same way. The proportionality will be split across multiple rows because there'll be more than one series at middle level. But you'll have multiple rows of these, multiple columns, sorry, of the P vector for each of the middle out series. But you can still write it down in the same way. It's a little more complicated. So I haven't actually chosen to show it here, but it is possible to do it. And then when you put the G matrix into the same equation, you'll end up with it disaggregating down and aggregating up.
Thank you.
Not a problem.
These are not probably right.
Okay, so we've established that each of those methods can be written in this way. So therefore, we can then, one of the nice things about doing things mathematically is once you can write things down generally, then you can derive things for all of the different approaches simultaneously. So let's see what we can do with this notation. We could take the mean, for example. So the mean of the forecasts, whether it's top down, bottom up, middle out, are just going to be S times G times the mean of the bottom forecasts. And so that's going to be S times the expectation of the bottom forecasts, provided we have this condition, and that condition is going to be important going forward. So if provided that happens, then our new forecasts are going to be simply the sum of the bottom level forecasts. And they're going to be unbiased if those bottom level forecasts are unbiased. So it's a really neat and simple result that shows that provided our original forecasts are unbiased, however they're obtained, then we only require that S times G times S is equal to S, and we will get unbiased forecasts. So this creates a condition on the G matrix that ensures we've got unbiased final forecasts. Now, question is, does this thing actually hold for the types of models we're looking at? We'll come to that. But it gives us a condition that says for unbiased forecasting, provided we start with unbiased forecasts, we end with unbiased forecasts, as long as SGS is equal to S. Now, it turns out that that is true for the bottom-up method. It's not difficult to show. And it turns out that it's not true for any other method that we've talked about so far. It's not true for top-down, and therefore it's not true for middle out method. So even if you start with something that's unbiased, you will end up with something that's biased if you're using a top-down or middle out method. But if you're using a bottom-up method, at least you get unbiasedness. Doesn't mean they're going to be good forecasts. They still might have really high variance, but you will preserve the unbiased nature of the forecast. So that's an interesting first result. What about the variance is the other thing we can do. Well, we can take this equation and just say, well, what's the variance of the right-hand side? And just using standard matrix algebra, the variance of the right-hand side is going to be SG times the variance of our original forecasts times G prime S prime. So the WH here is the 8-step ahead variance of the original forecasts given like this. So that tells us a couple of things. Firstly, it tells us how to get prediction intervals, which up until this result, there was no, as far as I know, nobody knew how to do prediction intervals for bottom up or top down or anything like that. It is actually quite difficult to estimate this WH. So even though it's, you can write down how to get prediction intervals because you know what the variance and the mean is, getting them might be hard. It also suggests something that it depends on the G matrix. So we can't do anything about S. We can't do anything about W. That's just where the forecasts come from. We can do something about G because we're choosing that. And it suggests that maybe we could think about getting the best forecast if we could find a good G matrix. So something to think about. Okay, so that sort of brings us up to date to what was going on up until the reconciliation literature started. So when people talked about bottom up and top down, we now can have some properties. We know about some unbiasedness properties. We know about how to get the variance. Now let's move to what reconciliation really is all about. And I'm going to go back in time again and talk a little bit about where it came from. So here's a brief history of the what's happened over the last 20 to 25 years. So the idea for this came to me in a consulting project where I was forecasting Australia's labour market back in 2001. It actually didn't work very well, but not because reconciliation was a bad idea, it was just the nature of the problem. It turned out not to work particularly well for that problem, and there was another way we could do it better. Then I thought about this for a while, and then I had a new PhD student from Bangladesh, Roman Ahmed, and around the same time, I had a new postdoc by the name of George Athanasopoulos, who will be well known to you as the president of the IIF now, and now my boss. But at that stage, he was my new postdoc, and he was involved with forecasting Australian tourism for the federal government. That was what was funding the postdoc, and that was one of these hierarchical problems. So when Roman came along as a new PhD student, I suggested to George that we supervise him together and that he work on this hierarchical problem. Then a couple of years later, I gave the first presentation of it at a conference. And then a year later, we had a preprint of the first paper on how to do this, which co-authored, of course, with George and Roman. And it worked pretty well, but we had a lot of trouble getting it published. In fact, it took another 4 years before a journal would publish it. The referees, kept saying this is, you're not using any new information, and it was such a new idea, such a new way of thinking about it that nobody liked it. We did an application paper on Australian tourism, which got published in 2009 in the IGF, but the methodology still wasn't available. So the methodology, which sort of underpins the application, was not published. The application paper was in 2009. And we had written some software, so I put the software on CRAN, software we call HTS. And almost immediately, organizations around the world started using it. And within about a year, I estimated there was thousands of organizations using this approach to forecasting large collections of data, but still the methodology wasn't published. Eventually in 2011 it was. And then I moved on to other things, George moved on to other things, and we sort of let it lie for a while. And then had another PhD student come along, Shanika Wickramasuriya, and felt that there was still some theoretical things to be done here. So again, supervised by both me and George, Shanika worked on this problem and developed a lot of the theory, and that came out in 2019 in a JASA paper. By that stage, the top journals had started to take some notice of this, even though originally nobody was interested in looking at it. You can see the growth of the idea by looking at Google Scholar items. So if I do a search on the phrase hierarchical forecasting, nothing really before 2000. A little bit of a kick up here when we started, which was when we first started thinking about the problem. When our first paper came out in 2011, the first methodology paper that's here, and then it really took off after that. Forecast reconciliation was a phrase we came up with a little later, so it took a bit longer to take off. And now we're getting hundreds of papers every year on the topic. Another way of thinking about it is to look at the IIF program, the International Symposium on Forecasting. Here I'm just searching for the phrase, for the partial word hierarch or the partial word reconcile. And you can see that it's sort of taken off. It's pretty noisy, but it's taken off in the last few years. Okay, so that's the history of it, where it came from. And it's also why you'll see Australian tourism used a lot, because that was the postdoc that George was employed on. Okay, let's go back to this equation. Y tilde is equal to the summing matrix S times some matrix G, which depends on, how we're going to, something we can choose, and then Y hat's the original series. What's going on here is that we forecast the original series like this, and we could forecast all of them, or we could just forecast the bottom level or the top level. So for now, we're going to forecast all of them. G is going to combine them to get bottom level forecasts. So G is going to be some kind of combination, and then S is going to add them all up. And bottom up and top down can be seen as special cases. But think about it more generally, beyond bottom up and top down. G could be anything. We do, though, want SG S prime to be equal to S to preserve the unbiasedness property. And it turns out that if SG is a projection matrix, if this thing here together, is a projection matrix, then that will be true. So we can think of this in terms of projections, where you're projecting from a high-dimensional space to a low-dimensional space. And provided you are doing that using a proper projection matrix, then you're going to preserve unbiasedness. And we've seen that the variance is given by this formula here. Lost my mouse, there we go. Given by that formula there. And so the natural question is, how do you choose G optimally? How do you get the best possible G? So that was the question that Shanika Wickramasuriya looked at in her PhD thesis, and this was her solution, which we called MINT, for minimum trace. And the simple theorem is, if you do have a projection, then the trace of that variance covariance matrix is minimized with this choice of G. This is the best choice of G. The trace is an important thing because that's where all the variances live. So this VH is, this VH here is the variance covariance matrix. So down the diagonal of the variance covariance matrices is all the variances for all of the different series. So if we sum those variances up, we get a measure of how good our forecasts are over the whole collection. Okay, so the trace is the sum of all of those variances, the sum of the diagonals. So this tells us that that's the optimal G, the best G, that's going to minimize the sum of all of the variances. It's quite a simple result, quite a powerful result. All you need to do is to estimate WH, and you get the best possible forecasts. If you've done any, statistics using matrix algebra, you'll recognize that that looks a little bit like generalized least squares. And so one way of thinking about this is to think about it in terms of a regression problem. But we're mostly thinking about it in terms of an optimization problem. This is the optimal choice of G for minimizing the trace. So we then have this equation which says, however we start, wherever these forecasts come from, we can make sure they add up, we can reconcile them and get coherent forecasts by pre-multiplying by this, this object here, this matrix here. So this is called the MINT solution. It's L2 optimal amongst all linear unbiased forecasts. You just have to choose a WH, which is easier said than done, because that's a variance-covariance matrix, which could be a really big matrix. And we don't always, we know what the variances are because they're the variances of the the 8-step forecast, but the covariances, the off-diagonal ones, they're the ones that are a little harder to estimate. It's not so hard to estimate it if H equals 1, because these guys are then just the residuals, and we have those for all of the different forecasts, all the different forecast models, all the different series. So we can compute the variance-covariant matrix of the residuals, and maybe that's a way forward. So the idea is maybe this WH, if we thought about it as proportional to the W1, maybe that's a good approximation. We know it's not strictly true, but maybe it's a good approximation. So that leads to a bunch of different ways to estimate this WH, or to approximate the WH. All of them making this assumption that WH is somehow proportional to W1. The KH doesn't actually matter because it's going to cancel out. Let's just see that that's the case. Because if I put the KH times W1 here and also here, because this thing here is inverted, they're going to cancel out because KH is just a scalar. So it doesn't matter what it is. All we have to do is to plug it in, and the W1 will take the place of the WH. So if we ignored it, if we said, well, W1 is the identity, then we get the ordinary least squares solution like this. If we said, well, it's diagonal, we'll ignore the off diagonals and we get the WLS solution like this, just by replacing the diagonals by the variances. Another diagonal matrix approach is this one, which we call WS structural, which basically just says if the bottom level series are all independent of each other and they all have the same forecast variance, then this is what you would get as the solution. So it simply turns into the structure of the problem, but it's assuming that they all have the same variance at the bottom level and that they're independent. So that they seem a bit unlikely, don't they? Because you're ignoring all of the off diagonals, and we, in a hierarchy, you would expect, the aggregates to be correlated with the disaggregates, so you know that there's some at least of the off diagonals and not zero. So ignoring them doesn't seem like a great idea. Or we could just take the sample covariance matrix of the residuals, and that gives us MINT sample. This fourth one here, this one. But if we have a lot of series, then covariance matrix of a huge lot of series is probably going to be singular because of these correlations that are quite strong. So that doesn't always work. And then the last one is we call MINT shrink, which is a shrinkage estimator to basically shrink towards the diagonal. So there's a question I see on the Q&A. There's a question, is there an easy to use Python package for this? Yes, there is. There's several. I'm actually going to talk about software in the very last lecture, the last one next week. But if you go to the the website that I gave on the first slide, which is robjhyndman.com/FR2023. I list there some software packages that do it. The one that I would recommend in Python is produced by Nixtla, Nixtla. It's very good. Okay, so we have 5 different solutions, and 3 of them diagonal, 2 of them allowing for the off diagonals. This allows us to get the y tildes. It doesn't actually help in getting the prediction intervals, because you do need the WH fully for that. You're not going to get things cancelling out. So it won't help us to get the forecast variance, but it will help us get the point forecasts. Now I said, well, you know, the diagonal ones didn't sound too bad. Sorry, I said the diagonal ones sounded like they were not a good idea because you're ignoring the off diagonals. It turns out that they're not as bad as you might think. And this is just a little demonstration why. If all of the base forecasts came from the same linear model, so suppose you just used a regression model for everything, or you used an AR2 model for everything and with the same coefficients, or any autoregressive model with the same coefficients, then the forecast errors are going to be coherent because you're using the same model. And then you can write down y hat is equal to S times B hat plus S times epsilon, and that epsilon is going to have this, but you're going to be able to work out the covariance matrix of that, and the WH is going to be equal to S times whatever that is, the bottom level covariance times S prime. And then when you work out what G is, everything starts cancelling out and you end up with an OLS solution, like magic. So if you did start with forecasts from the same model, then you end up with OLS. And that's probably not true, of course. You don't normally have the same model for all of the different series. You'll have different models. You might use different ARIMA models, or you might use different exponential smoothing models, or you might use some models that have covariates for some series, but different models for other series. But they're not going to be too far from giving you forecasts that are coherent. So it's not quite as bad as you might think, and it often actually works reasonably well. It was that result actually that was why the referees didn't like our paper. They described it as heroic assumptions. So let me do an example on the Australian tourism data. I'm going to use the Fable package for this in R, because I think it's the nicest interface and easiest to use. But as I said, there are other packages. I list several R packages and several Python packages on the website that I gave on the first slide. In Fable, we use Tibble structures. So a Tibble is a time series Tibble, and this tells us it's got 18,000 rows, 5 columns. It's monthly data, 1 month apart. There are 75 different series here for the different states and zones and regions. So every row this is the number of visitors in thousands to, in that month, to that state, that zone, and that region. We create the aggregates using this notation. So we go aggregate key, state, nests, zone, nests, region. So regions are within zones, within states. And then I'm just going to sum over the things below, and I create all of the aggregated series. So the original data is just the most disaggregated level. So now I've got 110 series. And I'm going to fit an ETS model to each series, a different ETS model to each series. So this comes back with 1 row per model. And you can see, for example, that ETS MNA is fitted to visitors to the Canberra region, whereas an ETS MNM is fitted to visitors to the Central Coast region of New South Wales, and so on. So different models for different series. Then so I'm going to store that in this object called fit. And then I'm going to take that fit object and I'm going to say I'm going to reconcile in 5 different ways. I'm going to try the 5 things that I just talked about, OLS, the 2 different diagonal WLSs. This one's commented out because it's going to give me an error. Mint covariance, just doing the sample covariance matrix, and mint shrink, using a shrinkage estimate of the covariance. And I'm going to forecast 2 years ahead. So you can see the nice interface allows me to use just natural language notation. 2 years as quotes, and it'll interpret that to be 24 months. And it comes back with a forecast for each model, for each of these different types of reconciliations, as well as the original type model that I started with, and for each region and for each future period of the 24 months. So I now have 550 series and giving me 13,200 forecasts in total. So in a few lines, we get all of that. Let's just have a quick look at what they look like. And you can see that the reconciliation doesn't move them much. The original series is in orange, which is sort of buried in here. The original forecast, sorry. The data is in black. The original forecasts are in orange. The mint shrink ones are in blue. You can't quite see there, but you can distinguish the green ones, which is OLS here. The WLS structural ones are the pink in there. So they're pretty close. That's for, so that was for the whole of the country. That was for New South Wales. That's for Melbourne, where I live. That's for the Snowy Mountains region, which is the most seasonal series in the collection, and so on. So each of these series, we have the original forecasts and the different types of reconciliations. Now I'm going to check how the things went by calculating the mean absolute scale errors on a test set. So that's a 2-year test set, and the root mean squared scale, that's mean absolute scale errors, that's root mean squared scale errors. And then I'm going to compute that for all of the different series. So here's, with the accuracy command, I can do that very quickly to get all of these for all the different models in every region. That's a little too much information. I'll need to summarize. So let's group by the model and just take the average mean absolute scale error and the average of the mean squared scale errors. I square them and then take the average and then take the square root, so it still can be interpreted as a root mean squared scale error. And I get this. So this is the original forecasts are here, which didn't add up, so they're not particularly useful. They're just there for comparison. And then the 4 different reconciliation methods that I've used are here, and they've been ordered by which is the best. So the best is at the top, OLS, followed by WLSS, then the mint, and then WLSV. Overall, every reconciliation method is better than the original forecasts, and that is pretty consistent. Generally, reconciliation helps because you're adding some structure. You're saying that these forecasts have to add up to these other ones. So reconciliation sort of gives you a little more structure, and that forces the forecast to improve. What about if I did it by level? So which approach works best at the national level? If you're only interested in one level, you might only be interested in national or state, but not so interested in the other levels. How does that work? Well, so let's group by level and by model, and then we get this result. And so you can see that for all the levels, so there's national, there's state, and so on. OLS is better for all the levels except the original national series. So at the top level, the base forecasts work a little better. But for every other level, OLS is better. And the further you go down, the more reconciliation is improving. And again, that's pretty general result too, that the more reconciled So the more disaggregated you go, the more reconciliation is helping. And that makes sense because they get noisier and noisier. And so the signal at the higher level you can use to improve the forecast at the bottom levels. So I just wanted to finish by talking about a couple of computational tricks. I'm going to skip over, because I want to leave a little bit of time for questions. I'm going to skip over the first couple, which are sort of there because they're interesting mathematically, but they're less useful practically. Let me skip to the most practical way of doing this that's fast, that helps a lot. So I'm just going to go through these slides to this one, and that's to use sparse matrix algebra. So these matrices can be big, and that S matrix, you've got one row for every single series in the entire hierarchy, and they can be millions. And you've got one column for every series of the bottom at the bottom level. They could also be millions. So this is an enormous matrix. Matrices that are millions by millions obviously have billions of cells, and even storing that can be tricky. But it's sparse. That is, it has lots of zeros in it. And so you don't actually have to store every single element. You just have to store the elements that are ones and where they occur. Similarly, other matrices, I haven't talked about the C matrix, but we'll talk about that tomorrow. But other matrices, the W matrix is also sparse because a lot of these series are not correlated with others. And so you do get lots of zeros in that W matrix. So because they're sparse, we can more efficiently store them, and we can also more efficiently compute these linear equations using a famous algorithm from the 1950s due to Lanchach, which actually the idea was good, but it was numerically unstable in the first, the one that he proposed, but it's been extended, and the version by Page and Saunders from way back in the 1980s works really well. So this was proposed in that first paper, the 2011 paper. Also, I found out much later, was proposed completely independently by Tommy DeFonso and his co-author Marini in the same year, not for forecasting, but for reconciling time series when you've got lots of series that want reconciled rather than forecasts that want reconciled. And using this algorithm, I can reconcile 2 million series in 20 seconds on an old laptop, like a 10-year-old laptop. So it's really fast. The slow part of forecast reconciliation is not reconciliation. The slow part is forecasting all of those individual series. But because we're doing them independently, that's embarrassingly parallel. You can throw it onto 1,000 cores and bring them all back. So actually, computationally, this is not a tricky thing to do. As long as you implement it using good algorithms and sparse matrix algebra. If you just use brute force, you just programmed it up using the equations as they have been given, then of course it's going to fall over quite quickly. Okay, let me stop there so we have time for some questions. The three main papers that I've talked about today, the original methodology paper is the first one there, with me, Roman, George, and we brought in Hanlin Shang to help us finish it, another postdoc. Then some of the fast computational stuff was in another CSDA paper in 2016. And the real theory part, and probably the most important paper in the entire literature so far, is the paper by Sharnika, Wickramasuriya, and George and I, which appeared in JASA in 2019. Let me stop there. Happy to take some questions. Now, I see there's already one from Sarah. So I think you can probably see it, but let me read it out for the purpose of the video, because it probably won't be there. The question is, for reconciliation in the overall forecast pipeline, do you apply all the other tricks first, e.g. for each series, base, intermediate levels, and total, make a pool of multiple forecasts, trim, select the top forecast and average, then put those results through? No, we do not do that. What we do is we just forecast all of the series regardless, ignoring any constraints for all of the top level, middle levels, bottom levels. We just forecast everything. and then we apply this reconciliation procedure to get the final forecasts. And it's better than top down, it's better than middle out, it's better than bottom up. The question is, which of the various W matrices should we use? That's really the only question to need answering. And that, as we've seen, depends a little bit on which level you're at, and also how strong the covariances are. So if you've got really strong covariances, then generally you'll need to use one of the methods that estimate the covariance matrix, like mint-shrink or probably mint-shrink. If you don't have such strong covariances, then you can often get away with using a diagonal matrix. Okay, Jeff's asking, I'm curious if you've seen good results when performing reconciliation using machine learning models as the base versus using a univariate statistical model like ETS. Yeah, it really doesn't matter where the original forecast come from. You could fit a neural net to everything and then do the reconciliation. So that's not the problem here, actually. Use whatever method you think works for the data sets you've got. Obviously, fitting individual ETS models or individual REMA models is more computationally efficient because you can parallelize it. But if you've got a pre-trained neural net, then that can also be computationally efficient to do the forecasting, not computationally efficient to do the training, but to do the forecasting. That can work. So where the forecasts come from is not really the important point. Hanlin Shang is asking, so he's the last author of that first paper on the screen. He's asking, the shrinkage W estimator in MINT may relate to the Ledoit and Wolf covariance estimate. Okay, I don't know that, Hanlin. Thank you for the pointer. Let me go to the next one. So Leonidas is asking, when you have a big population of time series to forecast where some of them will be seasonal, some of them won't be, how do you select whether you use the seasonal variant of MACE or root mean squared scaled error or the simple one? That's a good question. Look, if some of them are seasonal, I will usually use the seasonal variation, but I haven't actually thought very much about the consequences of that. Maybe if you've only got weak seasonality for some series and none for others, it might be better to use the non-seasonal variant. It is important to use the same method for all of them. But I guess, just speaking off the top of my head, it's probably about how much seasonality there is and how strong it is in the series where it occurs. Sukanta, what happens if one or more of the disaggregated, that is the most disaggregated series, has lots of missing data or is noisy? Can you still use it? Yes, you can still use it. If there's got lots of missing data, then you'll need to use a method that handles missing data, which there's lots of time series forecasting methods that do. It often is very noisy, which is one of the reasons we're doing forecast reconciliation, is so that you can get the benefit of the signal at the higher levels and apply it at the bottom levels. So yeah, it can still work. It's actually an open question whether you really want to disaggregate down as far as possible. There's some interesting new research which is about, maybe you should not include all of the disaggregations. And I have a postdoc working on that. But in principle, you can still apply it no matter how disaggregated things go. So this relates to the last question on my screen. No, not the last question, the one by Mark. Does it make sense to reconcile partially? For example, I just want to reconcile forecast results for a zone within Melbourne. Would I still need the bottom level forecast for other cities or only city level forecasts and above? So you can certainly reconcile partially. You do have to be careful that the S matrix spans what you're interested in. So you have there's sometimes a minimum number of forecasts that you'll need to include so that the reconciliation can actually work, or you'll end up with everything being singular. but there's no, you don't actually have to include every series. You can remove, bottom level series that you're not interested in, and along with the relevant columns of the S matrix and the rows of the S matrix. Prince is asking, it may have been answered already, but if I missed, is it better to have individual forecasts come from a single type of model, or is it okay to have individual series get trained with any model that best fits and later reconcile them? So the nice thing about reconciliation is it doesn't matter where they come from. So you could have completely different models used for different series, and everything will still work. In the Fable package at the moment, it is assuming that everything comes from the same model. But that's a software constraint, not a mathematical constraint. They could come from anywhere. Savandi's asking, can you parallelize individual forecasts using Fable or the forecast package? Is the functionality for this inbuilt in the R packages? That's a good question. We do have some parallelization built in. I'm not sure that it's built into doing forecasts individually within this reconciliation step. I'll have to come back to you on that. There is some parallelization built in to both Fable and the forecast package. In the forecast package, it's to do with parallelizing the selection of models for a single series. In the Fable package, it's a little more flexible because we use the future package to do the parallelization. But I can't remember how easy it is to do that for the individual series on different processes, rather than for one series running different models to select the best series, the best model. So I'll come back to you on it next time.
Rob, there are a couple of questions in the chat as well.
Okay. Let me just go to them. So Angie's asking, since forecasting at any level except the bottom level leads to biased forecasts, do you reckon always using bottom level? So that's not quite true. Top level and middle up forecasts, sorry, top down and middle up forecasts are biased, but any of the projection methods I've talked about, including any of the MINT methods, they're unbiased because they're projections. So I would recommend doing that. I would recommend using all of the forecasts for all of the series, not just bottom level, because you'll get better results. You'll get the strength of the top level series, the signal in the top level, and you'll get better results overall. The only reason that I introduced bottom level at all was because bottom-up forecasting at all was because that's where the literature was 20 years ago, and I wanted to give some historical context, but I certainly don't think you should be doing that now. We have much better methods. Tao's asking, while the reconciliation is optimal for L2, any thoughts about other penalty functions such as L1? The thing is, L2 is sort of the natural one to use here, because it's mean, the mean is the solution to an L2 optimization. So means add up. So if you're doing L1 optimization, you sort of get this disconnect because L1 optimization is going to be optimal for medians, but medians don't add up. So you're not really going to end up with something that's properly coherent. So although you could write down L1 reconciliation, I'm not sure that it would give you something that makes sense. Sebastian's asking, would it be appropriate to use bootstrap residuals to generate prediction intervals? Yes, exactly. We're going to talk about how to do that in the probabilistic reconciliation lecture, which is number 3 in the series. So same time next week, we'll do that one. Marty's asking, one main idea behind hierarchical forecasting is to generate coherent forecasts because we want to make consistent decisions across different levels. Do we know if these coherent forecasts lead to coherent decisions? Yeah, good question, Marty. So if you're forecasting, at national level and state level and store level in some retail thing, and you're using those forecasts to decide something or other about allocation of resources, then you do want them to add up. So it makes sense from a decision-making point of view. And I'm going to give examples of that next week. Whether that's actually how it works in practice, I don't know. I don't know if people are doing this so that they end up with coherent decision-making, and whether the decisions are coherent. It's a good reason to do coherent forecasting, is so that you can make your decisions coherent, but whether people actually are using it in that way, I'm not sure. The feedback I'm getting anecdotally is people are using it because it gives you better forecasts, so improves forecast accuracy. It also helps improve coherent decision-making, but I don't know whether that's a justification. And I think I've run out of questions. And I'm well over time, so we probably should stop there.
Yeah, thank you, Rob, for this excellent lecture. So I can't wait for the next one. Whoever registered will be getting the link to the next lecture as well. So thank you, everybody, for coming, and thank you, Rob. Thank you, George. We'll see you in a couple of days. Okay. Bye, guys.